Welcome! So now we're going to look at orthogonality. And so remember that this is with respect to an inner product. And in many cases that inner product happens to be the dot product. So let v1, v2, etc. to vn be non-zero vectors in an inner product space if the inner product of vi and vj is 0, if and only if I equals j, then v1, v2, etc. to vn is an orthogonal set of vectors. Let v1, v2 to vn be non-zero unit vectors in an inner product space V if the inner product of vi with vj is 0, if and only if I is not equal to j, then those vectors form an orthonormal set of vectors. Okay, let's have a look at an example. And so orthonormal here requires, in addition to those being orthogonal, that they are also unit vectors. Okay, so let's have a look at an example 9.14. Let v1 be 1, 1, 1, v2, 2, 1, minus 3, and v3, 4, minus 5, 1. Show that the set v1, v2, v3 is an orthogonal set of vectors. But let's go a step further and show that it's not orthonormal because they're not unit vectors. Okay, you can see that they're not unit vectors because their norm is not equal to 1. So what we need to do here is take the dot product. So here we assume in this special case that the inner product of vi with vj is the dot product. Okay, but it's not always the dot product, right? The inner product is more general than the dot product. So let's take the dot product of each of these vectors. So v1 dot v1 is, and I'll just transpose these to take their dot product. So we have 1 plus 1 plus 1 is 3. That's not 0. Okay. v1 dot v2 is equal to 1, 1, 1 dot 2, 1 minus 3. And that's 2 plus 1 minus 3, which is equal to 0. So these two vectors, v1 and v2, are orthogonal to one another. So v1 dot v3 is 1, 1, 1 dot 4 minus 5, 1. And so for that we get 4 minus 5 plus 1, which is 0. Okay, so v1 and v3 are orthogonal. Now we haven't yet taken v2 dot v2 whoops, 2, 1 minus 3. Okay, so we have 4 plus 1 plus 9. It's 14, that's non-zero. And then v2 dot v3 we haven't yet taken. So we have 8 minus 5 minus 3, which is 0. Okay, then the last one we have not yet taken is v3 dot v3. So 16 plus 25 plus 1, which is 42, isn't it? And that's non-zero. Okay, so what we found then is that each of these is orthogonal to each other when I is not equal to j. And so we have an orthogonal set of vectors, so let's write that down. All right, let's move on to the next page. Okay, so on this page, let f be on the interval, or this be a vector space of functions on the interval minus pi to pi. Let this be an inner product space of functions with inner product given by the definite integral, or 1 on pi times the definite integral of the product of f and g. Show that the set is an orthogonal set of vectors, and find an orthonormal set of vectors. Okay, so we want to show that the integral of, let's write this out first. Okay, so cos of nx inner product with cos of mx. So this is 1 on pi times the integral from minus pi to pi cos of nx times cos of mx. Okay, now this integral should be 0. Now I'm sure there's an angle addition formula that we could use for this, but I'll just calculate this here. Let's see if Mathematica will do this. Okay, so Mathematica gives us this right here, so we can save a little bit of effort in actually calculating that integral. But I'm sure what you would have to do here is use an angle addition formula, most likely. All right, so let's pull out the 2 that we have there. Put it out here. So then we have inside 1 on m minus n sine of m minus n x plus 1 on m plus n sine of m plus n x. And these are inside that sine function, evaluated from minus pi to pi. Okay, so next what we do is we sub in pi and minus pi. So now if m and n are not equal, let's say if m is not equal to n, then our inner product here would be 1 on 2 pi. Now since we're putting in pi here and m and n are integers with this not being equal to 0, we have 0 plus 0 minus 0, because sine of an integer times pi gives 0. So this will be 0. Now, if m is equal to n, then we wouldn't get this integral, would we? Because that denominator would be non-zero. So let me put in an n here. So that's the integral of cos squared of nx. All right, so up here I should really say first assume, because that's the way we calculated that, m and n are not equal. Okay, and now otherwise this inner product looks like this. So we have 1 on pi x on 2 plus sine of 2nx on 4n minus pi to pi. And now if we sub in pi and minus pi, we have 0 for the part where there is a sign, but over here it's not. So what this will be then is 1 on pi, pi on 2, and then minus pi on 2. And so that's pi on 2 plus pi on 2, which is pi. The pi's cancel, and we get 1. Okay, so this right here is an inner product. All right, so let's move on to orthogonal matrices. The square matrix Q is said to be orthogonal if the column vectors of Q form an orthonormal set. So the dot product between the columns is 0 if we're not taking the dot product of a column with itself. Then it should be 1. Okay, theorem. An n by n matrix Q is orthogonal if and only if the inverse of Q is the transpose of Q. So let's have a look at example 9.16. For any theta in the set of real numbers, the rotation matrix cos theta minus sine theta cos theta is orthogonal. Okay, so what we'll do here is let's let U be the first column. So cos theta, sine theta, and V be equal to the second column minus sine theta, cos theta. And now let's take dot products. So U dot U is cos theta sine theta dot cos theta sine theta. So that's cos squared theta plus sine squared theta, which is 1. And also V dot V is minus sine theta squared plus cos squared theta. And we simplify that and have sine squared theta plus cos squared theta. Again, that's 1. Okay, now let's take U dot V. So cos theta sine theta dot minus sine theta cos theta. And so we have minus cos theta sine theta plus sine theta cos theta. And so these are opposites, and so that adds up to 0. Okay, so Q is orthogonal. Furthermore, notice that Q transpose times Q. All right, so let's write the transpose so you see what this is. I'm changing rows into columns and columns into rows. So the transpose of Q is cos theta minus sine theta in the first column, and sine theta cos theta in the second column. And now I just copy down Q again. Okay, when we take that product, we get the identity matrix. The 2 by 2 identity matrix, 1, 0, 0, 1. Again, because cos squared plus sine squared is 1. Okay, theorem 25. Let Q be an n by n orthogonal matrix. Then the column vectors of Q, as in the columns of Q, form an orthonormal basis for Rn. Q transpose Q is the identity matrix. Q transpose is Q inverse. And the inner product of QU with QV is the inner product of U with V. So this is the matrix Q times the vector, column vector U in item 4. Okay, item 5, the norm of Q times V is equal to the norm of V, where the norm of V is defined as the square root of the inner product of V with itself. So notice if the inner product of U with V happens to be the dot product, then what this says here is that the norm of V is the square root of V dot V. Okay, which is what we would expect. Okay, let's move on to the next page. Orthogonal matrices and QR decomposition. So now we'll consider QR decomposition of a matrix. Recall that the square matrix Q is orthogonal if Q transposes Q inverse. QR decomposition involves writing the original matrix A in the form A equals an orthogonal matrix Q times R, where R is an upper triangular matrix. This is a useful technique which can be used to solve linear systems, invert matrices, calculate eigenvalues, and more. QR decompositions are defined for non-square matrices too. If A is an m by n matrix with m greater or equal to n, then Q is an m by m and R is an m by n. So we'll stick to square matrices for this discussion. Furthermore, if A is invertible, then the QR decomposition is unique if we require that the diagonal elements of R are positive. Okay, applications of QR decomposition. The QR decomposition is useful in many elementary tasks in linear algebra. Suppose we want to solve the linear system AX equals B, and presumably it's somewhat large, so you wouldn't just do that with Gaussian elimination, for example. If we calculate the QR factorization of A, then we can write this as QRX. So this here is A, right? So let's write that. AX is QRX, which is B. And then since Q inverse is Q transpose, what we're doing here is multiplying by Q inverse on the left, but that's Q's transpose. And so we have Rx is Q transpose B. And so if we have such a QR decomposition, then we can easily solve for X by back substitution. This does not involve finding the inverse of a matrix or using Gaussian elimination directly, so it can be faster. Likewise, if we want to invert A, we calculate its QR decomposition, and immediately we have A inverse is R inverse Q transpose. which is quite nice. Again, because R is upper triangular, it's much easier to invert than a general matrix. We can use QR decomposition to calculate eigenvalues. A popular way of computing the QR decomposition is to use the Gram-Schmidt process, which you should know from computing an orthonormal basis. Well, we haven't done that. I'm about to show you how this works. So we'll use the process to compute an orthonormal basis of the column space of A, and it's well known that a concatenation of orthonormal vectors forms an orthogonal matrix. So this will be our Q. By this construction, the kth column of Q depends only on the first k columns of A. This gives R the required upper triangular structure. But we'll see this right here in the description of the algorithm. Okay, so that brings us to the Gram-Schmidt algorithm. So what goes in? An n by n matrix A, so a square matrix. What comes out? An n by n matrix Q and an n by n matrix R, where A is equal to Q times R, Q is orthogonal, and R is upper triangular. And this is the routine, but I'll describe it to you from the point of view of 3x3s, because it's just above trivial in size, but it's not too big. Okay, so what we do is for the values of I from 1 to n, we let A subscript I be the ith column of A. So in other words, A is equal to lowercase a1 concatenated with lowercase a2, etc., up to an. And so what we do then is we set, now this should say uppercase U, so you might want to change that, uppercase U subscript I is equal to A subscript I minus the sum of dot products multiplied by the vector V subscript K, where V subscript K is gotten via this. Okay, so once we have this and this, for all of the I from 1 through n, we can then construct our orthogonal matrix Q just by concatenating the column vectors V1, V2, and so on. Okay, into Q, and then R is obtained just by a bunch of dot products, but you can see it's upper triangular, zeros below the main diagonal. All right, but let's just talk about this in the case that n is equal to 3. So if n is equal to 3, then what are we looking at here? Well, we would start with I equals 1. Okay, then if we do that, we've got uppercase U1 is equal to A1, and then minus, now notice where the I is, the top of that sum is 0, but the bottom starts with 1. So there's nothing there to sum up, right? Because the top is lower than the start. All right, so then we would move on to this part and calculate that V1 is U1 on the norm of U1, and in this case it's A1 on the norm of A1. Okay, so with that V1, we're now able to calculate the next U. So this is I equals 2. So we have U subscript 2 is equal to A2 minus, now notice the top of the sum is 2 minus 1 is 1, the bottom is 1, so there is something in that sum. So this is the sum from k equals 1 to 1 of A2 dot VK and then times VK. Okay, since there's only one thing in the sum, we sub in that k equals 1 and simplify. So we have this, all right, and so this is U2, and V1 is right up here. Okay, so once we have U2, we're now able to calculate V2, which is U2 over the norm of U2. And once we have V2, we're now able to calculate U3. Okay, so U3 would be, now this is I equals 3, so that's A3 minus the sum from k equals 1 to 3 minus 1 is 2 of A3 dot VK times VK all right, and then let's write out this sum. So this is A3 minus, now we put in k equals 1 and we have A3 dot V1 multiplied by V1 and then A3 dot V2 for k equals 2 times V2. Okay, and from there, remember this is U3, we would then calculate V3. Let's fit this in the column. V3 is U3 over the norm of U3. Okay, so at this point we should then have V1, V2, and V3, so we just glue these together and form our matrix Q. Now it will be orthogonal. All right, so to see that this works, firstly, it's easy to see that all the VI have unit norm, right? Because look, the way they're designed here, they do have unit norm because we have divided away the norm to get a vector of norm 1. So by construction, they're all orthogonal. Suppose V1, V2 to Vi minus 1 are mutually orthogonal, then for j less than I, ui dot vj is given by this, we're just subbing that in, and then we expand the dot, and we end up with ai dot vj over there, and vj dot vj. All right, so this dot product will give us the square root of the norm. And since that norm is 1, all right, so this piece is 1, and so we just have ai.vj minus ai.vj, which gives 0. So Q is indeed orthogonal. By construction, AI can be expressed as a linear combination of the VKs for k equals 1, 2 through I. AI is this sum of scalar multiples of the VK, multiplying VJ for j less than or equal to I, and using the orthonormality of the V's gives us ai.vj is cj times vj.vj, which is cj because this dot product is 1. And this shows us that A is equal to Q times R. All right, now for the example. And so you can ignore the top of this, right? So let's just talk about the example. Find the QR decomposition of the matrix 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay, so remember we need to set this out as the concatenation of 3 columns. And so let's say A1 is 1, 1, 0. A2 is 1, 0, 1. A3 is 0, 1, 1. Okay, let's follow the routine. And I might need to find that where I put this on the floor. Okay, give me a sec. So you want to flip back and look at this in the case that n is equal to 3. So keep that here. But you should also look at it. All right. So what we are going to do first is, since n is 3, it's easy, right? Okay, start with I equals 1. So according to this, we have U1 is A1, which is the first column of the matrix A, so 1, 1, 0. All right, next we need to construct V1 by taking the norm of this. Now you can see that the sum of the squares of those entries is 2, and so the square root of that is root 2, and so V1 is U1 on the norm of U1, which is 1 on root 2 multiplied by the vector 1, 1, 0. So this is our V1. All right, now that we have that, let's move on to I equals 2. So now with I equals 2, U2 is equal to A2 minus A2 dot V1 times V1. Okay, let's sub this A1 and V1 in. So A2 is the vector 1, 0, 1. And then we need to take a dot product of 1, 0, 1 with this vector V we just got. And then multiply the result by the vector V1. Okay, and simplify this. All right, so this vector is 1, 0, 1. Now this dot product is, so 1 times 1 is 1, 0 times 1 is 0, 1 times 0 is 0, so we have 1 times 1 on root 2, so that's minus 1 on root 2, 1, 1, 0. Okay. And there's another 1 on root 2, so that gets squared. So then we have a 1/2 here. So I'll pull the 1/2 out of the whole thing. Right, 2, 0, 2, minus 1, and minus 0. Okay, so we have this. Now let's simplify that. That is 1/2 of 1 minus 1 and 2. Okay, so this is U2. And now that we have U2, we can construct V2. So let's take the norm of this. So the norm of U2 is the square root of the sum of the squares of the entries. So we have 1/2 squared plus minus 1/2 squared plus 2/2 is 1. So 1 squared. Okay, so that's a quarter, that's a quarter. So 2 quarters is 1/2. This is 1. So 1 1/2 is 3/2. So root 3 on 2. All right, and so now I need to divide this vector by 1 on root 3 on 2. So V2 is 1 on 2 root 3 over root 2, but I'll put the root 2 on the top eventually. Oops, that's a 2, isn't it? Yes. Okay, and so I put this on the top, and then I cancel a root 2 that's in this 2. And so what we will get then is 1 on root 6. 1 minus 1, 2. And this is V2. So far we have the first 2 columns of the orthogonal matrix Q. Okay, let's move on to V3. So I need to start with U3. Okay, so U3 is A3 minus A3 dot V1 times V1 minus A3 dot V2 times V2. Okay. Now A3 is 0, 1, 1. A3 dot V1, let's have a look. Well, we should probably just put this in, right? So 0, 1, 1 dot 1/6 1 minus 1, 2 times, for now I'll just write V1. And then A3 dot V2, 0, 1, 1. Oh no, that's V2 there. That's V2 there. Okay, so I've got to change this because V1 is what I need there. Right? Yeah, V1. So 1 plus 1 and 0. And this down here should be 1 on root 2. Okay. All right, so now A3 dot V2. V2 is this. So 1 on root 6. 1 minus 1, 2. And then times V2. Okay, so let's simplify these 2 dot products. So this dot product here is, so we have 0 times 1, 1 times 1, and 1 times 0. So this gives us minus 1 on root 2, V1. And so now I will fill in V1. Okay, then over here we have a product minus 1 plus 2. 2 minus 1 is 1 over root 6. So minus 1 on root 6. And then multiplied by V2, but V2 is 1 on root 6. 1 minus 1, 2. All right, we need more paper. So let's move over to the next page. So here U3 is 0, 1, 1 minus 1/2, 1, 1, 1, 0 minus 1/6, 1 minus 1, 2. Okay, now I want to have everything over 6 because 6 is the least common multiple of those fractions denominators. So I'll put this all over 6. Then we have 0, 6, and 6. Now if we multiply the top here by 6, having factored out the 1/6, then we have 3, 3, 0. And then here, subtract 1 minus 1, 2. Okay, so let's simplify this then. So 0 minus 3 minus 1, and then 6 minus 3 plus 1, and then 6 minus 0 minus 2. So we have 1/6 of minus 4, 4, 2. Okay, and so there's a common 2 I can get rid of. Put this over 3. And there we go. Now we have the vector u2. Okay, fantastic. So the last thing to do would be to construct V3. So it's 1 on the norm of U3 times U3. So we need the norm of this vector. So the norm of U3 is the square root of the sum of the squares of the entries. So minus 2/3 squared plus 2/3 squared plus 1/3 squared. So expanding that, we have 4 plus 4 plus 1 is 9. So the square root of 9 over 9 times 3 is 27. If I did that right, so no, it's all over 9, right? Yeah, it's all over 9. Is that correct? So 4 over 9 plus 4 over 9 is 8 over 9, plus another 1 over 9 gives 9 over 9, which is 1. Okay, so the norm of that vector is 1. That makes it easy. So then V3 is equal to 1/3 minus 2, 2, and 1. Okay, let's concatenate those three vectors together to form the orthogonal matrix Q. So Q is V1 concatenated with V2 concatenated with V3, which is, where did V1 go? Okay, so we've got 1 on root 2, 1 on root 2, 0, when we take this and multiply the root 2 in, or the 1 on root 2 in. Okay, now let's find V2 and do the same thing for that. We have 1 on root 6 minus 1 on root 6 and 2 on root 6. And then finally, V3 minus 2 on 3, 2 on 3, and 1 on 3. Okay, and hopefully this calculation was done correctly and we actually have an orthogonal matrix. So that Q transpose is Q inverse. So that would be what you would want to do next. So check that Q transpose is the same as Q inverse, and probably do that by multiplying. by multiplication rather than actually computing the inverse of that 3 by 3. So you would calculate Q transpose times Q and hope to get the identity. So see whether we get I. If we've done the calculation correctly, then we'll get I. If we have not, then we will not get I. All right, and then to get the upper triangular matrix R, you just take the dot products as was shown in the description of the algorithm. All right, and that's it for now.